module is an entity in Verilog where we describe a subcomponent of the system. At the center, we will have the HDL code describing the behavior and logic of the module. We will also have ports along the outside that we can use to connect this module to other modules. Once we have described a module, we can instantiate it as many times as we want. Let's write a simple module in Verilog. We start by writing the keyword module. Now, the next thing that we have to do is actually give our module a name. Let's call this one simple in and out. We then have some brackets where we define the ports for our module a little later. We then close those ports off with a semicolon. And that's kind of the starting section of our module. After this section, we'll actually put some HDL code that describes the behavior of our module. Then when we have finally described all the behavior of our module, we end the module with a keyword, end module. Okay, so now we have a bare bones module. Let's actually make it do something. We'll want to take in some input signals into our module. So let's have 3 input ports. In that ports list section of our module, we're going to declare these input ports. The first thing that we need to do for each port is state its direction. So we need to state whether it's an input port or an output port. Then we state logic, which is just another way of stating that this is a wire. We give the port a name, and then we move on to the next port, separating the port declarations with a comma. We wanted 3 input ports in this design, so we will do this 3 times, giving each port a unique name. Along with the input signals, we probably want some sort of output signal for our module. Let's have 2 outputs, out_1 and out_2. In a similar way to our input ports, we can define the output ports. However, this time we change the direction of the port to be an output, not an input. Great, we now have a shell for our module with some ports defined. The next thing we need is for our module to do something useful. Let's add some logic into the middle of our module. Let's make it so that out_1 is the AND of all the input signals, as out_2 is the OR of all the input signals. So just a quick refresher. For the AND, we only want the output, in this case out_1, to be high when all the input signals are high. Here's a truth table for a 3-input AND gate demonstrating this. You can see that when A, B, and C are all high, that is the only case where the output Q is high. As for out_2, we want it to be the OR of all inputs, meaning that the output is high whenever any of the inputs are high. And so here's a truth table for that. And here we can see that the output Q is only low when all the inputs are 0. To do this in Verilog, we will use the ampersand symbol for ANDing all our signals together, and the pipe signal for ORing them. So we can write this to assign out_1, and we can write this to assign out_2. Now, unfortunately, this won't quite work. It doesn't quite work like this. In Verilog, there are a few ways to assign signals to other signals. We'll cover those later on in the course in quite some detail. Now, to assign a signal like this in the body of a module, this is called a combinatorial assignment. Don't worry too much about knowing what that means at this stage. But in order to do this type of assignment correctly, we need to use the assign keyword before the actual assignment. So we'll add that in here. There, we have now made our first System Verilog module, given it some input and output ports and written a bit of logic in it. Let's test to see if this works. So in the directory where we had just written that file, type make. You can see it goes through and it compiles it and then it actually runs the simulation here at the bottom. This looks good. Now you'll see here that there's a bunch of stuff that got printed out while it's simulating. So we can see some of the output signals have been printed. This is by some logic that we refer to as a test bench. The test bench is a top-level System Verilog file that generates input sequences and put them in a log file, things like that. So it's sort of like a bit of wrapper logic that isn't necessarily part of the circuit, but that we just use for testing the circuit out. If you're curious, you can look at the test bench that we're using for this example. It's in our main folder here for this lesson. in top_tb.sv. But for this video, we won't worry about its contents too much. We'll look a little more at test benches later. What we will do now, though, is open a waveform viewer so that we can see those signals changing in our circuit. To do this, open GTK Wave and navigate to the file produced by the simulation. It should be in the main lesson folder, waveform.vcd. And so we open that, and then we can actually look at all the signals. Now, we need to navigate on the left-hand modules panel here to find our module in the hierarchy of the design. So we go through the test bench module top_tb, and there we can see our module, simple in and out. We then tell GTK Wave to display the signals of our module and those input and output ports that we specified on the waveform screen by right-clicking and going to Recurse Import and then Append. This will add all the signals from our module to GTK Wave. So we can see that we have our 3 inputs, in_1, in_2, and in_3, and our 2 outputs, out_1 and out_2. We can also see that the test bench is driving the input signals and changing each one of them. If we look at out_1, we expect this to be high when all the input signals are high. It's ANDing them all. And when we examine the waveform, we can see that this is the case, so this is working correctly. And also for out_2, we expect it to be an OR of the input signals. So it should only be low when all those signals are low. And looking at the waveform, we can see that this is correct also. Great. So it looks like our module is working correctly. Well, that concludes this lesson. Next, I'd like you to try the exercise to modify this code and experiment about with the waveform viewer. Okay, see you next time.